Okay, so that's the idea. Okay. So now, even more formally, let's define a symmetric encryption. So we're going to define symmetric encryption. And remember that at the end of the day, encryption is nothing more than software. Okay? I mean, it's software. It's code, right? You're going to write some code. That's why we're going to do some Python examples. Just, Python is a lot easier than looking at the SSL code. And it's just basically for understanding. We're going to start with a very basic cipher type, like ciphers before Second World War, which were ciphers that were just, what are called substitution or things like that, ciphers. And then, the more modern ciphers that are still in use today. All right, so we're defining now symmetric encryption. We kind of looked at it, kind of informally over here, and now we're just going to make it a little bit more formal by defining several things. So I'm going to define that there is now E, which is the encryption algorithm. Okay, so this is going to be our encryption algorithm. Okay, then again, we have Alice and Bob, and they just need to communicate securely. So we're going to assume here that the communication is going to take place in that direction. Okay, although it can be in any direction, just for the way I'm writing this. Then I have the decryption algorithm over here. So I'm going to have an input, which I'm going to call usually M, and that just stands for plain text. So plain text. So this is, in its simplest form, as you will do it on the CBM, is nothing more than a text file. Create a little text file, you write on it. Like I said, I like to do a test, and I'm sure we can do it virtually, where you have to get an A in that test, you have to decrypt something. So I'm going to give you a problem, some code and things like that, and on your report, you have to actually tell me the message that I wrote in there. If you don't tell me the message, you don't make it. So you have to understand everything that I'm doing to encrypt that. And I'm not doing anything complicated. It's just using these primitives. I kind of, it's like playing a little game, if you will. All right, so once I have the message is the plain text. What I want to do is I want to encrypt it, right? And I want to create the cipher, which usually is referred to by the letter C. And the cipher is basically an algorithm E, the encryption algorithm, which takes as input K, right, comma, M. And the output of that is C, right? So that's the output of it. So let me erase that. All right, so this K, of course, is that shared secret that I was talking about. You have to have it. No, without K, you can't do anything. On the other end, on Bob's side, Bob also has a decryption algorithm, and if you will notice, Bob wants to get the original message, M, right? So to do that, Bob will use a decryption algorithm given K and the cipher. And that algorithm will return M, the original message, okay? And so that basically means that Bob also needs to have the K. So in symmetric encryption, if Alice is in North America and Bob is in Europe, and they need to establish a communication, they're spies or something, right? So they need to send, spy information via the internet. What's the problem with this scenario? What's the problem with it? If you somehow they're spies, but
they have to get to keep
different locations. One another. What's the problem with this scenario that you can see?
They have to get the key to one another?
They have to get the key to one another. Exactly. So how do they exchange that key? What would you guys recommend? They're spies, right? So what would you recommend? What do you think? Just intuitively, what would you do?
Have like a face-to-face exchange of a USB or something?
Face-to-face, right? So that's what we think of right now. And before all of this, right? Before, let's talk about like probably the Second World War, the Enigma machines and all of that. People needed to have these little books, right? So I think what they did is they had a book, and the book, the key changed every day. So they had like a calendar, and they would say, okay, today is this date, and so they would look, oh, the key for today is this. With that key, they were able to break their algorithms, right? Because they had some kind of a encryption technique. Very good. So that's one of the challenges. How do we exchange the key? Right? That secret key. How do we do that? So that's one of the primitives that we will talk about. So remember, here, right? One of the primitives of this is we have to figure out how to exchange that secret key to achieve certain goals, security goals. And so that will be part of our, part of the primitives that we need to learn. Okay. Now the secret key here, what is the secret key? The secret key is nothing more, because at the end of the day, it's going to be digits, right? It's going to be a binary, zeros and ones, a whole bunch of zeros and ones. It really doesn't matter what it is. It should just meet two conditions. Okay, and then we'll show why, but really just two main conditions. One of them is the size of it. All right, you want it to be as big as possible, but obviously you can't have a key that is as big as the universe, right? That would not work, or even a lot less than that, because the computer would not be efficient. Imagine a movie, be very inefficient to do a lot of operations with things that consume a lot of memory. So it needs to be of a specific size. Usually, you will see, measurements 128 bits, for instance. That's how keys are measured. You'll see, oh, it's a 256, byte or bits or something. The other condition is that it must be random. Now, can you achieve 100% randomness on a computer?
No.
No, right? You cannot. And that presents a problem because computers are deterministic. They're pseudo-random. So even an algorithm that you think is really good, it's only pseudo-random, right? So, but to achieve perfectness in security, you need perfect randomness, or that's your goal anyway. Nobody achieves it. So really in a sense, if you measure the security systems, you're almost saying that they're not 100% secure, but they're good enough. That's kind of the intuition that you probably want to get there. Okay. All right. Let's keep going. All right. So now there's a few other things that are important. I talked about E and D, right? The encryption and the decryption algorithms. Those are the encryption algorithms, okay? And you might, I don't know, this might surprise you, maybe not, but the algorithms are not obfuscated. It's not like you hide them. This is not like every company has a different one. In fact, the encryption algorithms, are publicly known. okay, are publicly known. I mean, and when it is said that they are publicly known, it means that they are really well known. You know, AES and DES are some of the most well-studied algorithms in the history of computing. They've been studied extensively to try to understand, because people, the goal of people is to try to break them. Imagine if somebody was able to break SSL right now. Nothing would work. The day that somebody breaks all of those, finds a way, easy way to break them, you know, our whole digital society would end, right? Because you wouldn't be able to do secure transaction. People would steal your money. You wouldn't be able to send emails. People would read your messages. You wouldn't be able to go to Netflix. People would steal your movies, you know. So your Amazon, you wouldn't be able to shop online because everyone would be, you know, stealing your information. And so really, the algorithms have to be studied really well, and they are. So in fact, whenever you use something that is really well studied. For instance, you know, we'll be using OpenSSL in Linux, which has everything. You know, OpenSSL will have literally all the primitives, and that's really what the labs are about. And so they're well known. There's nothing to hide. What you must, though, keep secret is your key. Keep as a secret. So, you know, I've already said this, but so E is the encryption algorithm. So E is the encryption algorithm, and D is the decryption algorithm. Right, decryption algorithm. And the only secret is this one. Okay, that's the only secret. The key or K. Any questions so far, guys?
Not yet, I don't think.
No. All right, so okay, so now let's move on then. So then, you know, kind of in summary, the core of cryptography is two things. One is the secret key, what is called the secret key establishment. Secret key establishment, right? And then secure communication with the established key. Secure communication with the established key. Okay, so that's the basic core of cryptography. So now that we've talked about that, let's go ahead and define symmetric ciphers. Okay, so you know, I usually don't. You know, some people in books, even in the Seed Labs book, they'll start with like substitution ciphers and then build on that. I think, you know, I'm just going to start with symmetric ciphers, but in one of the labs, there is a problem where I'm going to ask you to do a substitution cipher, and you'll just write the code. We'll discuss it in the class. Should be really fun to figure out. And you'll see, you know, my goal with that problem is to show you that even though it's highly insecure, that's not secure at all, but it is actually pretty difficult to code. So that's really the goal. All right, so symmetric ciphers. I really like cryptography. It's so much fun. All right, so symmetric ciphers here. Okay, so let's start with a definition. So remember, I've kind of said there's symmetric and asymmetric there's symmetric and asymmetric encryptions, right? So this is the definition of it. Definition. So a cipher, that's the first thing. You'll hear me refer to that a lot. And so we need to provide a formal definition of that. So a cipher is defined as a pair of efficient algorithms. And they are E for encryption and D for decryption. Okay, so there's usually two of them, but they work together in some way. There's actually one operation, I think I already talked about it. What was that operation?
XOR operation.
All right. No, we'll do an example of XOR today. And XOR, because computers are really good at XORing, right? Because it's bits. So you take, you know, a transistor, sequence of bits, right? And then another set of bits, and you can just perform an XOR operation and you're done. You flip that bit to something else. And so they're really fast at it. And so it makes sense to build cryptographic systems around very efficient operations. You don't want to, you know, have some very complex operation that would take forever, and then it would be unfeasible to use it. All right, so now that I've done this, so a cipher is defined as a pair of efficient algorithms, E and D, where E, K, M gives you the cipher, okay? And D, same K, but now that cipher gives you back the original plain text message, given the consistency equation, which is really simple. The consistency equation, and that's just going to be D, K, right? Now, in the place of, instead of C, we're just going to have, well, C is equal to EKM, right? So it's just going to be EKM, close the other parentheses, equal M. So that's the consistency equation, because we know that we take the original message with the key, we encrypt it, that gives us the cipher, and then the cipher with the key and the decryption algorithm gives us back the message. Okay, so that's really our definition. Oh, I forgot a parenthesis. That's our definition of what we're doing. So really, symmetric ciphers are, a cipher is defined as a pair of efficient algorithms where EKM gives us cipher and DKC gives us the message, given the consistency equation, which looks like that one. Any questions so far? Okay. Looks like there's questions. Okay, no questions. So, okay, sometimes these algorithms in the encryption, for instance, we talked about the initialization vector, the IV, right? And so they will have maybe an additional parameter, right? Which is the initialization vector, and it's really just like another key, not a key that you have to keep so secure anymore, but just a key that provides a little bit more randomization. Okay, a little bit more randomization. We talked about this last week. Okay. So now let's introduce